Hello everyone, thanks for watching this video. I'm Gang Chu from Tongji University. I'm going to introduce our work titled Joint Relation-Based Human Pose Estimation. This is joint work with Chi Xie, Jiewen Wang, and Shuang Liang. Human pose estimation is the fundamental for many computer vision tasks such as human action recognition and human-computer interaction. It aims to detect precise locations of each person's body joints like shoulder, hip, and ankle in a single RGB image. Recent years, the continued development of deep convolutional neural network methods achieve noticeable progress on human pose estimation performance. However, there still remain a lot of challenging cases brought by person-object occlusion or the multi-dwarf of limb joints. After analyzing the results of some state-of-the-art approaches, we find it obviously more difficult to localize limb joints such as ankles and wrists. Take the approach of Xiao et al. As an example. On MP2 dataset, the detection accuracy is 79.6% for ankle joints and 83.2% for wrist joints, much lower than the total accuracy of 88.5%. Human limb movements are ever-changing, and there can be various of candidates' joint positions in the images. Another challenge for human pose estimation task is to localize invisible body parts. Occlusion of person and person or person and object may occur anywhere. In the figures left, most body parts of the man are occluded by the little girl. Middle, the whole left arm and leg of the woman are occluded by the big boy. Right, the horse covers the left leg and arm of the little girl, and the left knee of the woman is occluded by herself. It will be extremely difficult to detect these invisible joints. Such cases are not rare. The detection of invisible joints must not be neglected. In real life, people also need to distinguish human pose with strange action or heavy occlusion. How do we human beings make it? We already know the structure of the human body. We can infer human poses by known body joint relations. In other words, we can localize a body joint by its neighbor joint and the human body structure. Computer vision is a significant task in artificial intelligence area. The mainly used deep neural convolutional network is also originally designed based on human neural activities. The mechanism of human distinguishing invisible body parts or limb joints should also be effective for neural networks. In this paper, we propose joint relation-based human pose estimation method to imitate this mechanism. The neighbor joint spatial relation is a vector pointing from selected neighbor joint to the joint for prediction. For limb joints such as ankles, wrists, and elbows, with small touches and inconsistent visual appearance, or invisible joints covered by other objects, it's very difficult, even impossible, to extract the features of corresponding area directly by deep convolutional neural network. On the final heat map, this will be shown as the low response value of the target joint area. This hard body joint cannot be found by searching the peak value to obtain the coordinates, or the joint position can be misjudged by the response value of the background area. In order to detect the joint position in the corresponding area, we must make the response value of the region reach the detection threshold. That is, let the region have the features of the target joint. In order to complete the above process of foregoing response value of limb joints and invisible joints, we need to teach the computer to understand the human body structure first. This can be achieved by setting neighbor joint pairs. Secondly, we need to know the direction and length of each limb. That is, the two-dimensional spatial relation of neighbor joint pairs. This kind of spatial relation is often used in previous bottom-up multi-person pose estimation methods, which shows that it is feasible to learn this kind of spatial relation through neural networks. Finally, we need a way to move the features of the selected neighbor joints to the touched area. Recent years, deformable convolution has been applied to enlarge the receptive field of neural networks. The mechanism of deformable convolution can also be used to move feature positions. However, the actual moving parameters are data-driven learned. This brings the bottleneck of huge computation burden. In our method, these moving parameters are generated from the feature or the image by joint relation subnet independently. We can accomplish this operation by a simple indexing algorithm. First, we find the neighbor joint area and get the joint relation vector information. Then we compute the target index of the features and use the new index to move the features. This feature moving step using neighbor joint spatial relation only needs indexing operation and no extra computation applied to the features. The overall workflow of proposed joint relation-based human pose estimation method is shown as a figure. The model takes an RGB image as input. A normal convolutional neural network is applied to extract the general features from the image. Then the general features are sent to the heatmap subnet and the joint relation subnet to predict the preliminary joint heatmap features and joint relation vectors. The trained joint relation subnetwork will imitate the known human body structure. The joint relation module performs moving operation on the preliminary neighbor joint features using joint relation vectors and produce the supplemental heatmap features. The preliminary heatmap features will be optimized by the supplemental heatmap features and output final prediction of human poses. The final outputs of the proposed framework is the joint position heatmaps and the joint relation vector matrix. We use MSE loss for the heatmaps. Previous experimental experiences tells us that if we directly use the L1 loss function to calculate the average error of the vector matrix V, the learned result is likely to be a matrix with all values infinitely close to zero. Therefore, we choose the weighted L1 loss function to generate corresponding weights for each position of the vector matrix. To confirm the effectiveness of proposed joint relation module, we perform experiments on MP2 dataset with different backbone networks, ResNet 18, ResNet 50, and ResNet 101. The base model is the same with the proposed model except the joint relation module. The evaluation results are shown in Table 1. We can see that models with neighbor joint spatial relation achieves higher prediction accuracy than the base models, especially for limb joints such as wrist and ankle. Besides, Table 1 also shows the evaluation results compared with recent simple baseline. With ResNet 101 as the backbone network, the detection accuracy increases 0.9% for ankle joints and 1.8% for knee joints by adding the proposed joint relation module, which shows its effectiveness on localizing limb joints. The proposed method achieves state-of-the-art performance. Meanwhile, we test the detection accuracy of invisible joints on MP2 dataset. As Table 1 shows, the prediction accuracy of invisible joints is much lower than the accuracy of all joints. The proposed method brings larger accuracy improvement for invisible joints, which verifies the mechanism of the joint relation to imitate the known human body structure. With ResNet 18 as the backbone network, the evaluation accuracy of invisible ankles can even increase 5%. Here are some comparison visualization results. The red points denote error-predicted joints, yellow points detect jitter-predicted joints, and green points denote right-predicted joints. The proposed joint relation module can help predict the occluded wrist, pelvis, and select the right head of the person. Here are some hard samples of human pose estimation results. The movements of these persons are strange, and our joint relation-based human pose estimation method can also get right poses. Here are some predicted joint relation vector realization. The proposed spatial relation model can learn the spatial relationship between selected neighbor joints from human body structure. To emphasize the improvements brought by proposed neighbor joint spatial relation and the feature moving operation, we perform ablation study with ResNet 18 as backbone network. In this experiment, we use another independent network with the same architecture as the proposed joint relation-based model to learn the beta joint relation vectors. The average loss of beta learned vectors dropped about a half. SR star denotes beta trained joint relation model. The beta learned joint relation vectors can better represent the human body structure. Thus, the supplemental features moved according to the joint relation vectors brings more accurate pose estimation results. In this paper, we propose a joint relation-based human pose estimation method to imitate the mechanism of human recognizing limb joints and invisible joints. The proposed joint relation model can play the role of known human body structure and help info accurate location of the complex joint by its neighbor joint. The joint relation-based method needs light extra computation costs and can be trained end-to-end. Experiments demonstrate effectiveness of the proposed method on different backbone networks. Thanks for your watching, and if you want to know more, please check our paper for details.